Hello friends, I'm Ashish Darbari, founder and CEO of Retimers, and to new listeners, welcome, and to the old ones, welcome back. Today in-house, I have a very exciting person. I was having a chat with him just before the podcast recording started, and we were discovering common roots. So without further delay, I would like to welcome Amin Shokrollahi, CEO of Kando Bus. Hello, Amin. Thank you very much for coming in. How are you?
Hello, Ashish. Thank you. I'm doing fine. Thank you very much for having me on your podcast.
No, it's a pleasure. Honor. It's a pleasure. I've been following you a little bit recently, thanks to Nanette Collins, and I was saying to her, look, we should find time to talk because we seem to have a lot more in common than what might appear in the first instance. So, hey, Amin, we're going to talk about what Kando does and what is your main USP in the business side. But I want to get to know you better, and I want my audience to get to know you better. So tell us about yourself. Where were you born? What is your journey to science and engineering? How did you end up where you are?
Sure. So I was born in 1964 in Tehran. That was a different time, a different government, different time. I was born into a, sort of a lower class from a society perspective, family.
So you had a class system back then?
Well, not really class, but, it was a somewhat a poor family.
Right.
So, my family apparently
economic
was
class,
back then.
Yeah, economic class, right? You mean? Yeah,
yes.
Yeah, fair enough.
But so my family realized around the time I was born, maybe a bit earlier, that the path to better future is education.
Mm-hmm.
So they kind of made everything happen so people get more educated. So an uncle, two of my uncles are math professors at this point. And one of them took it upon himself to teach me math when I was a kid. To give a flavor, when I was 5 years old, it's not about sort of counting, right? It's about real math. So he was teaching me axiomatic set theory at the age of 5.
Oh, wow.
So,
okay.
Yeah.
And that is in 1969. So at that time, set theory was not as, commonly taught as it is nowadays.
That is right. So he was teaching it to his students in the university, and then he was using me as a guinea pig in a way. And then very soon after, he started teaching me geometry, Euclidean geometry, because this is really the true thing of logic, right?
Right.
And giving me sort of geometry problems to solve, but he was never, if he gave me a problem, he would say, you will work on it until you solve it. I'm not going to give you a hint, nothing. You will do it. Sometimes I would sit on the problem for a week. Then, of course, you solve it after a week. You really feel happy. So I think that's what it taught me was you really need to sit through things and see them to the end. And so generally, he was also very scientifically interested. So this is how I got kind of into really math at the beginning and science later. So the first 4 grades, I was at a school in Tehran for gifted students.
Right.
It was, and then I switched to German school in Tehran. They had a program for purely Iranian students.
Mm-hmm.
To get them through to the end of high school.
Right.
And the promise was that at the end we would have 2 high school degrees.
Right.
One German one and one Persian one. And it was a fantastic school. It was really, so the school, of course, did also a lot. They realized that I am mathematically gifted. And they were offering me all sorts of programs. I think maybe in the US they call them honor programs or stuff like that. To go beyond what you usually would do in high school. And so, the German school system comprised back then 13 grades. So after the 13th grade, you had your diploma.
Mm-hmm.
So when I had finished the 12th grade, the new government, the post-revolutionary government of Iran, closed down the school.
Right.
But the school offered us an opportunity to go to Germany and finish high school, at least. And it just so happened that on the day we left Iran, the war between Iraq and Iran started. So a few hours after we departed, the airport was bombed.
Wow.
And all flights out of Iran were canceled.
So 1980 we are talking about this.
That was 1980, exactly, 22nd of September 1980. So when we arrived in Frankfurt, we thought, well, this is kind of a skirmish, maybe, it'll die down in a few days. It took 8 years.
8 years,
and
yeah.
about 1 million dead and injured for the war to finish.
It must be quite traumatizing for somebody at your age to have to, leave the country, and you're leaving for education, and then these political events
Yeah,
happen.
it was. At the same time, I was with my classmates. So it was fantastic. It was like a journey together. And this has bonded us in such a way that we still, to this day, every 2 weeks, we have a Zoom call on Sunday evenings. And then we kind of, and they're spread all over the world, right? And we talk, and we have a really good relationship, like family almost. All right, so I finished high school. Then I went to Berkeley for about 2 months. One of my uncles, the brother of the uncle who taught me all things, he was doing his PhD in math in Berkeley.
Right.
And I didn't have really money to stay in Germany for until my university studies started. So I said, why don't you come over here and stay with us for 2 months? And then you also see new things. And this is where I really understood. I absolutely love mathematics. The real mathematics, really how do you find these structures? How do you prove things, and so on and so on. And then, fortunately, I got a scholarship from the German government for my studies. I went back to Germany, and on that scholarship, I was able to finish my math studies.
So your PhD, I went for a PhD. So your PhD was from Berkeley, right?
Oh no, my PhD wasn't. I was in Germany, and my PhD was from the University of Bonn. But then I left for Berkeley as a postdoc. Right. So the first time I was in Berkeley, I promised myself I'm going to go back there.
Yeah.
It's a fantastic place. So once I got the opportunity to go there as a postdoc, I did that. And it was originally supposed to be a year, but then the year became 2, it became 3.
Right.
And later I went to Bell Labs as a member of technical staff.
Right.
And after 2 years, I came back to California again because I joined a startup called Digital Fountain as their chief scientist. So we were doing, data transmission over internet networks.
So which year was this?
I went back in the year 2000.
Right. Okay. So that was fairly recent, I would say, yeah.
That's right. So I went to Berkeley after my PhD in 1995. 1998, I went to Bell Labs. 2000, I came back to California to join Digital Fountain. 2003, I went back to Europe to join EPFL as a faculty.
Right, yeah, it's very well known, EPFL.
And then Digital Fountain was sold to Qualcomm in 2009. And in 2010, I sort of literally fell upon the ideas that gave rise to Kando.
I see. Okay. So what I find very interesting is you were basically a mathematician to the core from your very early years, 4 or 5 years of age. But you wandered into electronics quite naturally, which is not very common for mathematicians.
It wasn't very natural.
Huh? Well, accidents sometimes can appear natural, right? Especially the good ones. No, I mean...
Well, I'm not an electronics engineer. I mean, and I have to always tell my engineers, look, guys, I'm not an electronics engineer. Don't come to me when you have any electronic. If you have problems with math, I can help you. And what is really interesting is that if you know math very well, you can abstract things out and solve problems that you will never solve if you don't have an abstract view. And so that is really what I do for the engineers.
So this is amazing because I do formal verification, and I'm pretty sure you know what it is. And abstraction is the backbone of not just formal but also computer science, but also what you're doing in electronics. And it's not always taught to children and then students, and it's also not easy. And the context of abstraction shifts as you shift from domain to domain. And it's fascinating listening to you thinking a mathematician who's actually now heading a chip design company is focused on engaging with engineers with abstraction in mind, which is not quite it's not the norm. It's not what CEOs do, but very 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 fascinating. So let's jump to Kando. So you started Kando which year? Was it 2010? 2011. And
the ideas I had were in 2010. The company was starting to fund lab.
Possibly the ideas were festering for years, right? I mean, they kind
probably,
of...
yeah. Probably I mean, in a way, it was... So I was working with a postdoc on a completely different problem.
Mm-hmm.
Was designing channel codes, which is really my area of expertise for DSL lines.
Mm-hmm.
And he started telling me about differential lanes here, differential lanes there. And I what the hell is differential lane? And he explained it to me. So, you send 2 bits over, 1 bit over 2 wires, whatever. So I asked him, so what do you do if you send 20 bits? So, well, you take 20 differential pairs. So, well, there's just no way that this is efficient. Right? And, coming from a sort of a coding theory background, this is exactly, the kind of thinking. And this is exactly the transfer, right? You need to abstract the problem out. And then I understood that, well, if you do it something differently, you can do it in a much better way. And I was completely convinced that this is a known idea, that the industry has looked at it and so on. But we did a search and there was nothing like it.
So tell us a little bit more. So let's start from the beginning. So right now your company makes power efficient bus fabric. Am I right in thinking something?
Yeah, yes, that is a SerDes, if you will, but not a traditional one.
Right.
But the SerDes that does serializer, deserializer over a collection of wires, not necessarily 2.
And is it between chip to chip necessarily, or could it be within the chip itself?
No, it is really off chip.
Off chip. Yeah. So why did that struck a chord with you? Why not on chip? So why did you focus on chip to chip? And I mean, I know that chip to chip.
Well, the problem that my postdoc presented to me was off chip.
I see.
That's what I saw.
Okay.
But then later I realized the on chip. Fortunately, I didn't do on chip because on chip is in a way not more difficult to solve, but more difficult to bring to market, because you need to work with an EDA company to have it as part of their tool, so that when you place and route, etc., that it's all there.
Right.
And that's not so easy. I'm not saying off chip is easy, but on chip would have been perhaps even sort of more difficult in some ways to productize.
Right.
Yeah, this is really the reason.
So the off chip. So your focus is Highspeed SerDes protocol. Is that right, or is that a big family?
Yes, it's Highspeed SerDes.
Yeah.
And what we want to, when you step back, you look at this communication link, and you look at it from a point of view of a communication theorist, like I am in a way. And the first question you ask yourself is, what is the capacity of this channel? How many bits can I send per hertz, or whatever you're. And the striking thing is that when you compute this, you realize that what the industry is doing today is a factor of 100 sometimes lower than what you have as bandwidth. And still the industry is thinking, oh, maybe we should go optical, which is just so much more expensive. And I'm come from a frugal background, so why go optical when you have still such a long way to go to fill the capacity of electrical? Right? So then the next question that comes to mind is, all right, if the capacity is that, how are we going to get there? But the thing about Shannon's theorems is it tells you, what are the things you can surpass, but it doesn't tell you how to get there. So we have means of getting to the capacity of these channels. And of course, I know wireless very well through my time at Bell Labs, and I know how much importance was given to this in wireless. Why not wireline? It's a much bigger market.
So are you saying right now your company is the only company in the world making these products? Or is it because you have a niche in low power as well as high speed that gives you...
I wouldn't say we are the only company there are many companies that are building similar products. But I think we're the only company that is geared to, or that has this mindset that we want to get to capacity. And we are not necessarily bound by legacy. All other companies are bound by legacy. And they're trying to make whatever is legacy, just implement it better and, get...
So you basically started everything from scratch. So you find it a lot easier, clean slate. So there's this thing about your technology which has to do with retimers and redrivers. Can you explain to us what exactly are these and why are they relevant?
So these are, interestingly, they have nothing to do with this general SerDes that we are developing. It just turns out that all the methods that we have developed for our signaling can also be used in legacy signaling technique. And this retimer is based on kind of a legacy signaling. So why is it important? If you look at USB, and this is what we're looking at, the speeds of USB have increased or doubled almost from one generation to another. And USB 4, the latest one, allows you to send and receive 40 gigabit per second of data between two devices.
That's very fast, yeah.
That's very fast, right? And really on a pair, it's 20 gigabit per second. So you're sending very high frequency signals from the CPU all the way to the peripheral device. But the thing about these channels is that high frequency signals fade, they get lost. So there's no way you can go in one shot from your CPU to the peripheral device. Impossible. You need sort of chips in between that somehow work as a relay station. They take the signals, they recover the signals, and then they send it across the next segment of the link, be it the cable or whatnot, right? And so the USB Implementers Forum has recognized that this is a problem, and they're mandating the use of retimers. So in other words, if you don't have a retimer, you don't have USB 4.
Where is the retimer actually built? Is it built on the chip that is, like if I had a USB 4?
No, the retimer is just a discrete chip. And to think about it, every USB-C port of a device that wants to be USB 4 compliant needs one of these retimers. So then if you have an active cable, you find retimers on either end of the cable, and so on.
So given that the transmission is such high speed and high frequency, I mean, there's an equation with power, right? Which is higher the frequency, more power is consumed. So how do you then get into the power equation? Because a lot of the time the USB might actually be sucking out the power from the laptop or some other device.
That is correct.
Right?
That is correct. So there is power that is spent on the CPU, which is acting as the USB host. You don't have any control over that. This is the CPU companies have to do that. But on our end, all the design technique, we have about 400 patents, right? A large number of these patents are about implementation techniques of our own signaling. It just so happens that the signaling that's used for USB is a special case of our signaling. So we have put all our patent resources and the kind of things we have been doing over the years into this to make this as power efficient as possible.
Right. So I want to dig this into a little bit more. So do you end up then just designing the IP or the actual silicon?
No, we designed the actual silicon.
Actual silicon. And who is your end customer? Are you able to say these things?
Well, if you're obviously using a computer right now,
yeah.
chances are that the computer you're using to talk to me is one of our end customers.
I see. Okay, so that's pretty much entire laptop.
Laptop, desktop,
right?
Peripheral devices, and et cetera, et cetera.
And they're using one of the chips on the motherboard, basically.
Yeah, they will. I mean, right now the chip. Right now there are few systems that are supporting USB 4.
Right.
But very soon, next year already, you will find a lot more of those systems, and you will find our chips in those systems.
But what about USB 3? Clearly, you were also doing USB 3 before.
Yeah. The chip also supports legacy, which is USB 3.
Yeah.
And it supports Thunderbolt 3 and whatever else. Yes.
Right. Have you ever considered, given such high-speed communication is happening off-chip, I know it's slightly different, could any of this technology be useful for 5G or Wi-Fi?
I don't think so. And the reason is that it really depends on the noise of the nature of noise on these channels is what dictates the modulation. So our modulation technique is really geared towards the kind of noise you find in wired communication.
I see. Okay.
And so that's why, we can probably use it there, but, the techniques that people have developed for wireless, they're already pretty good.
And how big is this market for off-chip communication?
Well, if you take the entire market, that's really big. That's, it's definitely more than 100 billion. But obviously it's a total available market. And then if you look at the SAM, it's going to be a lot less. That is also why one of the reasons. So if you look at IP, you can be a successful IP company. There aren't that many in the world, right? ARM was one. And so what we did, we looked at this and said, well, what is the maximum I could possibly make on IP if everything went my way? Then what we realized was if we built the right chip, that one chip alone can make us as much money as our entire IP portfolio. So this is why we have expanded our business model.
And where are your teams based? Are they all in Switzerland or they're distributed in US?
No, we're distributed in Europe.
Okay.
So we have design centers, obviously in Switzerland, it's the headquarters, in Germany, in Denmark, several in the UK. And then we have people in the US. Remember, Jeff on this call is the US. And then we have sort of support and sales in Japan and in Taiwan.
Right. And I suppose the manufacturing part of it is all TSMC or one of these.
It's Taiwan, yes. It's TSMC.
Yeah.
Yes. So we pride ourselves in an amazing supply chain. TSMC being one of them.
So what I'm trying to understand and decode in my head is you have a very specialized product, and it is this one product that you make which is amazing. Do you ever think that you've put all of your eggs in one basket, and would it be also?
We're not doing that. No.
So tell me, what are the other baskets?
There are other products that are coming down the pipeline.
They are, okay.
Now that we know several things, we know how to build high quality chips for high volume production. This is not a skill set that you know. I mean, you have to learn it, and we had partners who taught us this skill set. So now we can go and build other things. And we know how to build retimers, and USB retimers is just one type of retimers. There are other protocols that also need retimers and products that we will come to market with. I can't give you specifics.
Sure, yeah.
Product roadmaps, I've understood, is much more protective of product roadmaps than of our technical details. So yes, there will be other chips that we are already designing them, and they will be coming to market probably next year for other markets. So the USB is consumer.
I see.
That is
device-to-device
communication for consumer. But much bigger market is of course servers, data centers, and networking.
So what is the typical time to market for this? So if you knew what you were designing on week number 2, how long would it typically take for you before it's production ready?
It depends a bit on whether the chip is mostly digital or mixed signal. Mixed signal is really hell on earth. It's very complex mixed signal chip. And our Matterhorn chip is mostly mixed signal. So if it's mostly digital and you just go down the normal product development path, especially with sort of our chiplet approach, you should be able to sort of have new products after maybe 12 to 15 or 16 months of design time.
Okay.
And then whatever time it takes to productize it, maybe up to a year after that. And then you have ready products for the market.
So it could be 2 to 2.5 years before it hits the market. And how much of this time, we are verification people, how much of this is verification time?
A lot. So, it used to be that for every digital designer, you needed maybe half a verification person. Right? Then the equation changed, was 1 to 1. It's now 1 to 2.
Well, it depends. For processors, Harry Foster's reported in December that it is for one CPU designer, you need 5 verification engineers.
Oh, even that. Yeah, possible. I think as you go into more advanced process nodes, it may become even worse. That's correct. But right now we work with for digital designers, at least 1 to 2. And then, of course, we have mixed signal verification as well, which, as you know, is a completely different beast. That number is not as large. And maybe it should be, but right now it's very difficult to find very good mixed signal verification people. Some of the verification task is actually laid upon the shoulders of the designers themselves.
I see.
But you really need a dedicated team of mixed signal.
And am I reading into this to understand that a lot of your verification challenges tend to be mixed signal rather than digital, and that's where a lot of the time gets spent.
For sure.
I see.
It is, we talked about abstraction, right? Mixed signal doesn't have the kind of abstraction that digital has. So therefore, verification is anybody's best guess. That's what I understand. If I mixed signal verification people are listening, my apologies.
I mean, mixed signal can also have abstraction, and you could consider digitizing, concretizing this analog domain, but it's not clear what the methodology should be. And is there any chance you use formal methods for your verification, or is it primarily?
As far as I know, we do.
Okay.
But I'm not myself a verification person.
Sure.
I tried to go a bit deeper and understand what they're doing, but very quickly I realized it's a second career. I can't. And it's of course at EPFL, where I'm a professor as well. I have very many colleagues who are experts in formal verification. I've been sort of talking to them to get up to speed. But yes, we do use form. But at the end of the day, we are also bound by what the tools can offer us.
I mean, for digital technologies, for problems that are purely digital, the tools are pretty good and very mature. And if you get the methodology right, you can get a lot out of formal. But I'm not sure if you want to share, but what, in your view, is actually the success rate of your first time turning around? Are you able to turn the chips around first time, or do you think does it take we've got it ready?
It will take multiple iterations for sure. I mean, I hope we will get to a point, in reasonable future that our first silicon is production silicon. And this is true for, I think, the more sort of digital chips we have, the more probable it is. But the mixed signal is just, to be honest with you, after I started this company, I'm amazed that the computers and telephones, whatever we're working with, they're actually working.
You're saying what I say all the time. I'm surprised the world is still working.
Yes.
Yeah, I think if you're an engineer and you know the complexity of what we look at, then it does beggar belief as to how we're still able to drive the cars and
it is true. I mean, look.
Yeah.
By designers, they design these mixed signal things, right? They have to take into account that every transistor is a random variable, right? It's a random variable, whatever, and then they have to design it in such a way that you get a yield of 99 something. And not just that, the temperature drops to negative 40 degrees. The transistor, you can't recognize something completely different. It goes to 120 degrees, something completely different.
I mean, imagine if your chip is deployed in Vancouver today.
For example, yes, exactly. Yes. So, and some of our, at least, in terms of our IP, they go to outer space. So the temperature requirement there is obviously very different.
And the effect of alpha particles and
that on top of it,
transient faults. But
how can they design it? I don't know.
How could you? And actually, what I really liked is you were so honest, and you said, you don't always get it right the first time around, which is very nice.
Not everybody says that. I know. It is true for almost all companies. You just don't say it. Believe me.
I know it is not something, but the complexity of chips is such that. I suppose when you reach a point when you're actually only spinning the run-of-the-mill designs, and then you can reach a point where you have a fixed point on verification methods. But if you're
for us, it's even more, right? So you a lot of it, especially for Matterhorn, that was an R&D project with a capital R. Right? So my engineers, they had to, because we put so many new things in there that have never been done in the industry before. And, my engineers were sometimes hating it, but I was saying, we have to. So obviously, something's going to give, right?
Yeah. I mean,
if you're doing standard stuff, then of course things are very different.
Well, what's the fun of only doing standard stuff in engineering? I almost lost track of time while talking to you, and I realized we've almost reached the half an hour. I mean, I don't want to lose the opportunity of asking you this question I always ask my guests, and I think you're one of the best placed people to answer this, given your experience in living in different continents and countries and also doing things so different. There are a lot of people who listen to our podcasts, I mean, who are students, graduate students, or professionals. And I always like to sample this from my guests as to what would be those 5 tips, if you can give us. What are the things these listeners should do in their early careers to be successful with engineering? I mean, it could be compute, it could be electronics. What have you got to say?
There's only one tip. I don't need 5.
Right. Well,
go for what you like. Find out what you like, what you're passionate about, and do that. Don't look at, oh, is Facebook hiring me? Is Google hiring me? Is Intel hiring me? No. By the time you're finished, we will see a completely different world. But if you do what you're passionate about, chances are you can do it very well. And if you're doing that very well, chances are that there will be many people who want to hire you after. If you want to go into a company, if you want to go into an academic career, even more. So find what you like and go for it.
So sometimes I have this situation, and I've seen with young people, they think they like something, so they go for it. But they actually don't really know how hard or complex this thing is going to be. And I often wonder, for experienced people, if we could actually give them a structured pathway into exploring different types of things, and then they discover that this is where their heart actually lies. I remember when I was 14, my mom was doing programming in C++, and because she was not giving me time, then I said I will never ever get anywhere close to computers. And I really never ever thought I would go and pursue computer science, never mind formal verification or whatever else I do. So sometimes it takes time, isn't it, to understand and appreciate, as opposed to following machine learning is the hype, so let's go with machine learning, right? And do you offer internships at Kando?
We do, yes, absolutely.
Okay. So if people wanted to work for you as an intern, they could actually go to your website and...
Well, not to the website. They probably have to contact me directly.
I see.
I'm easy to find.
Oh, okay. I see. Okay.
And we work with EPFL, for example, that is the university next door, and we have those programs. I think you're absolutely right about that. How do we figure out what you like? You have to obviously look at many different things. But one thing that is important is, you really have to have the stamina to go through hard times.
Yeah, well said. Well said.
If you don't have it, that is going to be very difficult to do anything.
Indeed. And schools don't teach you how to cope with failure. And
unfortunately, no. Unfortunately, there is one mathematician, one of my favorite mathematicians. His name is Leonhard Euler. Was a Swiss mathematician. And he's the only mathematician I know who also wrote up all the things that went wrong when he was trying to prove a theorem. And, when you go to his collected works, it fills shelves over shelves because he has all those. And this is at least as important as the methods that work.
Absolutely. Absolutely.
We don't do that. I mean, you can't write, if I write about the theorem and my attempts to prove it that were all wrong and send it to a journal, they will not publish it. Nobody will publish it.
No. And I totally agree with you. And I think this is a really valuable suggestion, is to make mistakes, document them, don't necessarily repeat them, but learn from them. Whereas my teacher in college used to say, once you're learning C, it's good you're making mistakes because you're learning. If you always wrote a program that worked, you would learn nothing, because you would then have knowledge given to you from somewhere else, not acquired in the field, as it were. Very well said. Very well said. And on that note, I think we can wrap up. And thank you very much for your time today.
Thank you very much for having me on your podcast.
It's a pleasure.
As I said, it's an honor. Thank you.
It's a pleasure. It's a pleasure. So, friends, I hope you liked today's chat. Do go to Kando's website. There's tons of very interesting stuff in there, especially if you're interested in high-speed off-chip communication. And as Amin said, he's very reachable, approachable, so you could find him on LinkedIn or from the website of Kando. And let's stay in touch, and we will be back soon. Thank you very much.